one is Rubik. It's a new open source project. And the second is QoS guaranteed for containers. Okay, let's continue. And before my sharing, I want to share you with openEuler and myself because I think they are very important as my background. Okay, the first one, openEuler. It is an innovative open source OS and covers all scenarios. That's our vision. And it has many innovations on Linux kernel and it is a solid cloud infrastructure. Currently, it is incubating and operating by the OpenAutumn Foundation. That's openEuler. It's an OS. And the second, myself, Jingxiao Lu, currently the project leader of Rubik project. And my focus is on container infrastructure and in Linux. So we have a connection on OS. So I will try to explain this topic, CPU utilization, from the perspective of OS. Okay? Why the resource utilization in data center needs to be improvement? As you know, our data centers are growing rapidly. That's why we have many data centers building every year. Then you know that the CPU allocation or reserved for the customer are very high in the data center. But if you check on the monitor system, you will find that the actual CPU utilization is low, maybe 10% or 20% on average. So in industry, we are trying many ways to improve the low CPU utilization. Okay. Currently in the container world, we are trying this co-located deployment to improve. Okay. Before that, we are in a siloed architecture. That means we have many different kinds of workloads, AI application, big data application. They are deployed in different resource pools with different software stacks. Okay, in these years we have Kubernetes. Okay, and most of our applications have already containerized and can be scheduled by Kubernetes. We have a unified cloud infrastructure these years. Okay, that's the basis of our today's topic, Kubernetes. We have a unified cloud infrastructure. Okay, and as to be, we define different stages for this evolution stages. The first one, level 0, independent deployment. That's the as-is stage at the last page, and the level 1 to level 4 are different stages at this 2B. Okay, that's something different between those levels. Okay, the first one, level 1, we define as shared deployment, and level 2 is hybrid deployment. The difference between level 1 and level 2 are we are already in the same software stack and share the same resource pools. The service type in the resource pool may be different. Okay, on level 1, maybe we only use the software, but the service type only one. Okay, and next in the hybrid deployment we have multiple service types. But at level 3, okay, at level 2 we selected the different kinds of service types in the same cluster. But at level 3 we hold that all workloads are deployed freely. From the OS perspective, we hold this, it is in the black box state, which means that we at the OS side, we have to detect which kind of workloads it is as a black box. Okay, level 4, we hold that it is in the whole multi-cloud deployment. We have a technology to schedule all kinds of workloads in all clouds to improve the whole CPU utilization. That's our different stages. Okay, based on the functions needed for the OS, I have listed many. Okay, those left part are for our operating system. We have multi-level resource isolation from level 1 to level 2. And from level 2 to level 3, they are QoS scheduling or quantification, interface control, or to level 4, the built-in capability. Okay, there's some key functions, and I will try to explain or introduce functions to you today. Okay, we have these functions, and we have this architecture. On the other part, upper part, they are Kubernetes in this cluster. We openEuler as a work node is located in lower part. It is built on Linux kernel, as I mentioned before. Then the Rubik is learned as a set in this Kubernetes cluster. Okay. It provides the different kinds of in here. That's our architecture. You can see that in this timeline, we have finished part of them, and we'll try to build more on this next year. Okay, that's our architecture. From level 1 to level 2, as I mentioned before, we are trying to build this multi-level resource isolation. Okay, why this it is not needed? Once we build this hybrid deployment for containers, they must based on a consumption that our workloads will be deployed with multi-level priorities. Okay, we have different priorities for those workloads. Okay, to simplify our modeling today, we called it, we divided it to two. One is on service, and the other time is offline service. The online service, they are sensitive to QoS and latency. Maybe they are for short time learning, and the offline service, they are offsite. Okay, so there are some difference on these services. So we define the different kinds of resource isolation capabilities for those workloads. As you can see in this table, we have CPU queues, memory queues, cache queues, network queues, and these queues. Okay, we have built such technologies, and they are all already open source in openEuler. Okay, I won't share all of them today, but try to introduce 3 of them. They are our elite features. The first one, as I mentioned before, we have online and offline workloads, and normally the online service needs more CPU resources. And in our Linux kernel, we are using this CFS scheduling algorithm, and CFS is a fair scheduling. Okay, we cannot have a balance on online service and offline service, so we add this multi-level preemptive scheduling to CFS. So once the online service wants the CPU resources, we can suppress the offline tasks to obtain the CPU resources for online service. Okay, this is the first feature. And the second one is multi-level load balancing scheduling. Load balancing. Okay, and it is because once this online service is running about we may have many idle CPU cores. At that time, we can load balancing those offline workloads to the other CPU cores to decrease the number of tasks, context switches, and migrations. Okay, that's the first and second features. They are both on the basis of hybrid on online service and offline service. But what about if we have a hybrid deploy with online service and online service? Okay, based on the characteristics of online service, it will normally apply for sufficient resources. Okay, that means we will have low utilization on CPU at most of time. So we try to build this dynamic core affinity feature to try to overcommit CPU resources in C group. Okay, that's the features from level 1 to level 2. And welcome to level 3. Okay, level 2, as I said before, okay, we are using the customer selected workloads to deploy in the same cluster carefully. Okay, in level 3, we have a such mission that we hold the customer can hybrid workloads freely. As a black box from our OS point of view, so we build such method with offline training to get a model on such specific online workload. And we can use these models for our prediction on live network. Okay, for online training, we try to run this online workload in the test bed. We have different kinds of magic collection from Linux kernel or the hardware. And we run this online workload in high pressure. And then at the same time, we stimulate different kinds of pressure to this online workload and capture all kinds of interference is suffered. At that time, after the testing, we analyze these interference and the QoS of this online workload. We can get a model. Okay, then after many testings, we have these different kinds of modeling for our latent online prediction. After that, yeah, we have this library as I showed here, and then we have hybrid deployment with online services and offline services. Then we have this Rubik learning as a demo. It tries to collect all kinds of matches in the background and does many kinds of quantification for its QoS and analysis interference for online services all the time. Once it has got any kinds of interference, you try to locate the source of interference. Normally, they are from offline service. So if we located those interference from offline service, we can try to control it by everything those offline services to another cluster or another node, okay, or separate state for this kind of CPU resources. That's online prediction. And level 4, remember that we in level 3 we are deployed in one cluster or one cloud. But at level 4, we hold that we can use multi-cloud or multi-data centers. So the customer may face one scenario. He has a port request CPU cores down, he may get different computing capabilities among different clouds, which increases his management costs because he has to maintain different configurations in different clouds. Okay, why it has happened? I listed the possible reasons. Maybe it is by different generations of processors or different architectures of processors, or maybe they are using the same processor but with different configurations, such as HT or frequency, or different kinds of frequency. So we propose this idea. Can we unify the computing capability for this processor or for this physical server? So in our Linux kernel, in openEuler, we try to normalize the computing capability. And in Rubik, we try to conversion this capability to a unified NCU that's normalized computing unit for the easy management of this cluster, okay, for scheduler. Okay. That's all key functions we define for this utilization. For your easy using, we recommend that you use Rubik. It is a bridge connects our cluster, Kubernetes, and openEuler. It runs as a daemon set in Kubernetes cluster, okay, in the work node. You can quickly experience it with this. First, you fetch its YAML, and then you apply it on the node. Then you can integrate it. For more details, please visit our code repo. Okay. This is our first case. We already use our technologies in our internal cloud platform. In the sample cluster, we have already reached 70% CPU utilization. Okay, this is case 1 and case 2. Our community friend, Sina Weibo, they already use our features in their Leaf network in production. They already reached 60% more CPU utilization. Okay, this is our cases. And what's more, we recommend that you use Volcano and Kamada for more cluster features. As you know, for this CPU utilization, we are talking the whole data center or multi-cloud. But on openEuler and Rubik, we are based on the only specific node, okay? If you are going to the cluster or the multi-cloud, we recommend that you use Volcano and Kamada, okay? Welcome to JS. We are learning to CloudNative SIG and isula-build in openEuler. And isula-build is a lightweight container engine we developed in openEuler. And welcome to engage us. Thank you. That's all for today.
Thank you very much. Do you have any questions?
There was one slide about Rubik,
Yeah.
and at the bottom there was the frequency scaling. Yeah, this one.
This one?
Yeah.
Yep.
So what does Rubik give me? It gives me like a unified explanation of how much compute I get from that particular system.
Yep.
How does this translate to the CPU utilization? Because, for example, if I take the frequency scaling, right, and I enable the low P state P0, enabled, whenever whenever it goes into P0, just randomly I lose like 50% of the performance, and I add a bunch of latency also on network, even if it's not really sleeping, right? But how does what does Rubik do in this case?
Yep.
Or is openEuler already configured not to do these things?
This is a good question. Okay, the first thing, we are still trying to develop this feature, maybe on the late of this year or next year. Okay, and what we're trying to do is actually we are only focusing on the CPU resources now. So the first thing we are trying to learn a micro benchmark on Linux kernel or on the Linux. We try to test the capability of this CPU. Okay, we got a score for this CPU. Then we unified in Rubik. After that, we can get a result, maybe from 0 to 100. It's a score for this CPU. Then propose to the custom scheduler. Okay, at that time, it may introduce a confuse to the customer, because normally in our for our daily use, we configure different CPUs for our apps, okay, or for our container pod, maybe 10 CPUs. If with this one, maybe there's a number, but not the CPU cores you configure. But with this number, maybe you can get the same computing capabilities in different clouds. That's our reason. Any more question? Yes, we're trying to define a small benchmark to test the capability of physical CPU. Yeah.
Great talk, thank you. My background actually is performance engineering. I spent maybe 30 years doing this sort of stuff in grid environments. So
Yep.
I don't know if you have much familiarity with some of the earlier grid computing,
Yep.
resource scheduling stuff. This is quite close.
Yeah.
Maybe you might pick up some points, but this looks really interesting. So you're only trying to optimize you're not thinking about I/O and networking as part of the problem at this stage?
Sorry, I didn't hear.
So you're focused on CPU rather than I/O, which is also another resource in a
Yeah.
cluster, and networking, which is also another network bandwidth, which is another resource that you might find challenging at some point.
Do you mention this one?
Yes, okay. Make this guy I/O as well.
Yeah, I didn't prepare the PPT for this feature today. Okay, we are trying to use the EDT and eBPF in Linux and try to how to say just with EDT and eBPF and has a small config in the user space to control the network bandwidth. Okay, I think it's hard to describe it. Maybe I can show you something later. Okay. Sorry.
Another quick one. How are you building the model of the system and resources? Are you using some modeling language or tool?
Is that this one?
Yes. So what does the model look like?
Okay, we have this also is still based on the OS point of view. what we can see is different cases of resources such as CPU, cache, and memory. Different kinds of workload, they may, maybe I can take an example of Nginx, okay? Nginx, it is, most of the time it is only using the CPU, okay? So you have a specific model, it has a high CPU usage, okay? But it didn't sensitive to other resources. That's kind of CPU sensitive or CPU intensive workload. Yeah, that's one kind of model. Okay. And such as we have many, we can define different kinds of models, maybe network intensive model or such as. Thank you.
Thanks again for your talk.